What's up, everyone? Welcome back. And in this video, we're going to do some more reinforced concrete beam analysis. And in particular, we're going to do an example problem where we have to calculate the design flexural strength of a reinforced concrete T-beam that's given here. And I have some dimensions. The flange width is 36 inches. The total height of the section is 30 inches. And the depth to steel from the extreme compression side is 27 inches. And what this cross-section implies is that there's an applied or an ultimate moment here, mu, causing compression at the top, tension at the bottom. And the material properties, I have Fc prime of 4 ksi, Fy or grade 60 steel with Fy equals 60 ksi, and I have 3 number 10 bars to represent my area of steel. And that area of steel, this As, is just 3 times 1.27 inches squared, which is going to be 3.81 inches squared. From the given information, what I know is, or at least from the drawing here, I know that the width of the flange is 36 inches. The width of the web here, BW, is 16 inches. And the depth to steel from the extreme compression fiber to the center of the steel here is 27 inches. My approach to this problem is going to be the same as if I were analyzing any cross section for the nominal or the nominal moment strength and the design flexural strength, and it's going to involve the following steps. And this is how we're going to do it. We're going to draw the strain and stress profiles first at ultimate, and I look at that as drawing a free body diagram or schematic. And if you can draw this, you don't have to memorize any equations for this, for any beam analysis really. And the next thing we're going to do is apply force equilibrium to calculate the neutral axis depth, then verify some of the assumptions that we used in this force equilibrium step, and then determine the strength reduction factor, or this phi variable here, so that we can calculate the design moment strength. Then we'll calculate the nominal moment using moment equilibrium about some point on the cross section, and then just multiply that number m sub n by phi to get the design moment strength. So the first thing that we want to do is draw the strain and stress profiles at ultimate for the reinforced concrete section. And so for the T-beam, I've redrawn it right here. And the thing I like to do is draw horizontal lines for the top and the bottom, and have this vertical lines here. For the first vertical line will represent my strain profile, and then the second one will be my stress kind of slash force profile. But the thing to remember here is that you are drawing this strain and stress profile at ultimate. And what that means, this word ultimate implies a specific strain value for the compressive strain. And in this case, the concrete is crushing. And so here, that means the compressive strain in concrete reaches the ultimate compressive strain. And if you're using the American Concrete Institute standard, this is 0.003 in compression. And here I will have a linear strain profile, and that linear strain profile is always true. And here, when we draw this line out for the strain profile, we're going to assume for now that the neutral axis, more like the depth of the equivalent stress block that we're going to use for the stress profile, is within the flange. So what we're going to do is assume that the depth of the equivalent stress block is within the flange. And here's what the strain profile might look like that here. And this, where it's 0 is equal to, is where my neutral axis location is here. This would be C and A, and the depth and my steel strain would be here, this epsilon S. This would be my strain in the tensile steel right here, and that's something that we need to figure out. And the stress profile looks like this. If we're using the equivalent stress block here, or the Whitney stress block, I'm going to have a stress block that goes here down to a distance A, here, and here. This has a stress intensity of 0.85 Fc prime, and my steel, represented by the layer of steel location here, will have a stress over here of Fs. Okay, and you know what this depth A means, the depth of the equivalent stress block, is that my neutral axis is shallow enough, if you will, that my equivalent stress block depth stays within the flange region. right here. And so this, I'm assuming right now, is my area in compression. This has a resultant of, I'll call that C sub C, a resultant force, C sub C, and the steel has a resultant force, I'll call that T sub S in tension here. And there will be a centroid of this compression block, which will be this distance here, we'll call that Y bar, and the distance between the two, or the couple really, the tension and the compression forces, I'll call Z. And that's just another symbol for the arm right there. And really this comes out to D minus Y bar here. I would like to emphasize to you that this drawing here assumes that the depth of the equivalent stress block A is less than the height of the flange of this 4 inches, and so we have this nice rectangular compression zone. If this turns out to be not true, we're going to have to redo the formulation and probably modify this drawing a little bit to reflect reality, or reflect what's really going on. Alright, so the next thing I want to do is utilize my force equilibrium equation to calculate or determine the neutral axis depth, the C and A. The way I'm going to do that is just take some of the forces, the horizontal here, equal to 0, and that just tells me that TS is equal to C sub C. And if I assume that the strain in my tension steel has yielded, then my relationship here, I can substitute, and I can just have that this TS is ASFY is equal to 0.85 times FC prime times the area in compression. And so here I can solve for the area in compression, and this area in compression is going to be equal to ASFY over 0.85 FC prime. And if I substitute some numbers, that's just going to tell me I have, what, 3.81 inches squared times 60 KSI divided by 0.85 times 5 KSI. And that tells me that the area in compression is 53.788 inches squared. And as long as this area in compression that I need is less than the area of the flange, which I'll put in purple here, here is the geometry of the flange of this T-beam. As long as that's true, then this assumption is true right here. And so if I were to calculate the area of the flange, that would just be 36 times 4 inches, which is 144 inches squared. And that means that AC is less than A flange, so my stress, or my area in compression, is this red zone. It still stays as a rectangular block. And so I can say, therefore, because the area of the compression is less than the area of the flange, the area in compression I can now say is AC is equal to A times B, where A is the depth of the Whitney stress block, B is the width of the flange. And I can solve for A here directly now. So going over here to the left here, and let me scroll down a little bit. This A is equal to AC divided by B, which is 53.788 inches squared divided by the flange width 36 inches, and that tells me A, the depth of the equivalent stress block, is 1.494 inches. And then I can back calculate, because I know A is equal to beta 1 times CNA. I can solve for CNA, the neutral axis depth, which is going to be A over beta 1, and this will be 1.494 inches divided by beta 1. And in this case here, because I have FC prime equal to 5 KSI, beta 1 is equal to 0.80. And this gives me a neutral axis depth of 1.868 inches. Now the next thing I want to do is verify my assumptions. I went ahead and I verified that the depth of the equivalent stress block is less than this 4 inches, which was the height of the flange. But I have this other assumption here that I have yet to verify, and that's the tension steel has yielded. And so in order for me to do that, I can just go ahead and use similar triangles from the strain profile, which if you look over here, to calculate the strain right here, I would just have that this distance right here is D minus CNA. And by using similar triangles, I can come up with a relationship for the strain here as a function of the geometry and the strain in compression. So that relationship by similar triangles is epsilon s over d minus CNA is equal to epsilon c over CNA. And this whole thing just becomes that epsilon s is d minus CNA over CNA times 0.003. And if I substitute some numbers, I have 27 inches minus 1.868 inches divided by 1.868 inches times 0.003, and that tells me epsilon s is equal to 0.04. Now this number is much greater than epsilon y, and this number is greater than 0.005, which according to the ACI code means this is a tension controlled beam, and by that phi is equal to 0.9. And this is in ACI chapter 9. This is from ACI chapter 9 if you're interested in looking that up. And you'll see there a diagram that looks like this, and there'll be a phi value and epsilon t, which is just another way to say the extreme tensile fiber, and here this will be 0.005, and we are in this zone, which is the tension control zone, and this is 0.9 right here. Okay, but anyways, you can see some other videos and whatever that'll be all there, you know. And this is something you got to know, right? You just got to know it. You know, the reality is you just got to be able to look it up. All right, don't be weak. So we verified that the steel yielded, and now the next thing that we can do is calculate the nominal moment. And to do that, there's no memorizing equations here. You know, you just go back and look at that stress profile again, right here, to calculate the nominal moment. I look over here at the stress profile. I realize that my area and compression stays within the flange, so it's a nice little rectangle. So that means the depth of my equivalent stress block, the depth of the resultant C sub C, this is just A over 2. And so if I sum moments, and I like to draw this little MN here, if I sum moments about any point, and it's conventional to take moments about where the C sub C is, then I can solve for this M sub N right here. So let me show you what that equation might look like here. If I sum moments about C sub C equal to 0, and I say this is positive, I'll get an equation that actually looks like this: minus Mn plus Ts times Z equals 0. And that just tells me that Mn is Ts times Z. And because the steel is yielded, this is ASFY. Z is D minus Y bar. And because my equivalent stress block and the area and compression is still a rectangle, this Y bar is just A over 2. And now all I got to do is substitute here. AS was 3.81 inches squared. This yield strength of steel in this problem was 60 KSI. D was 27 inches minus A over 2, which is 1.494 inches divided by 2. And I plug and chug. Oh, let's convert this into kip feet. So 1 foot every 12 inches. And this number becomes 500.12 kip feet, right? And it ain't no thing, man. You just multiply it by phi mn to get the design moment strain. That's 0.9 times this 500.12 kip feet. And here, this is 450.11 kip feet. And gosh, you know, I think this is as deep or as challenging as the FE exam might get. And, you know, you can do it. All right. So hopefully you enjoyed. Take it easy.